My name's Evenchick. This is Eric Meyer. Yes, we are both Erics, and we are both working on the same project, which is Warpforge. And today we're going to be doing really the first introduction to this project. It's the first sort of public talk about it at an IPFS or PL event. So we're looking forward to sharing this with all of you in this Compute on Data track. So at a high level, what are we building here? Really simply put, it's a three-stage thing. So at the very input side, you have content addressable things going in. And these are some sort of input asset that you'd like to do some compute on. We treat these usually as file systems, as tarballs that get extracted. Then we have some execution that happens, and this happens hermetically. So we're doing execution in an environment that relies minimally on your host. And once that execution is done, you probably want to do something with the results. So we take those outputs and we also make those content addressable and usable in further execution or in next steps. And in terms of what this is for, these inputs tend to be things like the tools you're going to use to build software. So things like GCC, Make, and Bash if you're building classic Linuxy binaries. Something like Golang and, well, nothing else because Golang is pretty self-sufficient. Maybe it's a Rust tool chain, maybe it's Python, something along those lines, as well as any library code that you're going to need to build the tool. Then from that, we're going into the execution. This is also going to depend on your particular build chain, but at a simple level, it's something like make install, something like go install, running that tool chain. And what the output is, well, whatever you were trying to build. So if you're going for libraries, maybe that's ImageMagick. If you're at PL, maybe that's Kubo. Various things that you could put together here. But fundamentally, it's all about building software. That's the main approach. In general, you could run anything in the container, but the approach that we're taking right now, or the focus we have right now, is on building software. It's also part of a bit of a bigger ecosystem, and you're going to hear more about these items later today, so I'll introduce them up front. So Warpforge is the build tool. It takes some inputs, runs something, and spits out some outputs. We also have this concept of zaps, which is a way of packaging applications such that they're path agnostic, and we can run them from anywhere on the Linux file system. That sounds trivial, but it's actually harder than you might think, and there's a whole talk about it for that reason this afternoon. And lastly, we have this thing called WarpSys, which you'll actually see pop up in this talk, and this is a software distribution that we're starting to work on. So think of, Debian's got a bunch of packages as a software distribution. Arch has a big list of packages. Nix has a big list of packages. This is the foundation for starting to build up some of those packages such that they can be used in these types of builds in a path-agnostic way. So to execute hermetically, the main, the bedrock of this is to do all the execution in a containerized environment. So we use a container to do every piece of exec. And the real goal here is to eliminate the dependencies on your host system as much as possible. It's not possible to get rid of all of them for various reasons, but we can get rid of things like what your host file system looks like. And this is good because, well, for one, it means that I can give you build instructions and they should work on your computer as long as the tooling is running. And secondly, it allows us to work towards reproducible builds. This is the concept that we want to be able to have instructions that will allow us to build a bit-by-bit reproducible, exact same executable twice. And by putting all of our definitions for inputs, definitions for exec in a single place in a way that is not going to depend on your host system, this eliminates a lot of the challenges of trying to make things reproducible. So we're going to walk through how this tool works on the inside, and there's three high-level terms we need here. We have formulas, and this is the fundamental execution step. It provides a set of instructions to perform one step of a build. So it's inputs, something to do, and outputs. But writing these formulas by yourself without any help from a computer is quite annoying. So we have an abstraction on top of that called plots. And this allows us to have multiple steps and also allows us to use some other nice features that make this a lot more sane to deal with as a human. And then lastly, we have modules. This is just some metadata we attach to builds to say, hey, here's a name and some other data that you might want to keep track of. The formula is, again, this base level of execution. So all these inputs are content addressed, they're hashes, and they become paths inside your container. And that's really it. We're just placing these hash values inside a container at the input phase. We then run some exec. Currently, you can run a single command, or you can also write a script and have that whole script run. And then lastly, the outputs here, so the resulting file system. You can take parts of it or the whole thing, whichever you prefer for your application, and spit those out as outputs. And these end up getting hashed. It's a path and a type that you want to output, like a tarball. But again, formulas are kind of painful to write as a human. And the reason why is, well, this is sort of a deconstructed formula. This is really just a JSON object that's represented as. And when you see the inputs here, yeah, it's a big hash. And that's not an easy thing to keep track of without doing some copying and pasting or something along those lines. You're probably not going to want to do it by hand. But fundamentally, it's just these three things. So we have the input saying, I have a root file system I'd like to place in the container. That root file system happens to be a busybox binary that provides your typical utilities like SH, like a basic shell. You got echo, you've got CD, things like that. The exec step here, that's getting into actually running what we've brought in. And in this case, we're just running /bin/sh and running a very simple command to put the text hello into a file called /out/world. And then lastly, we might want to take that file and do something with it later. So we set up an output that picks just the /out directory, and we'll pack that up as a tarball. And that output is now something we have in our list of wheres that we can work with, and it can become an input to another formula. So some distinctions here over some other systems. The input is a map, and the keys are actually the mount path. So you can compose this however you'd like. If you'd like to bring in 6 different versions of GCC and place them all in different places for some probably terrible reason, you could do that. But it means that you don't need to build one big tarball, one big image, and load that. You can actually take different pieces and stick them together at runtime. And the outputs, well, that's also a map. You don't need to bundle up your entire file system. You can just say, I only care about this one binary. For example, with Go, you often care about maybe a handful of files from your output, but you may have brought in a lot of things to build it. You can just pick out what you want to actually save and save that instead of having to tar up the whole system. So again, manually writing hashes is not fun, and this brings us to plots. So one thing we realized pretty quickly is we need a naming system for inputs and for outputs. And what that became was catalogs. There's a whole piece that other Eric will talk about on that. But being able to assign real names to things is quite helpful. Also, multiple execution steps can be very useful. One example here is if you are building a large binary and you have some steps that build it and then some steps that maybe do some tests or move some things around. If that first step runs and then you want to modify one of the later steps, you'd probably rather not have to rerun the large build. So what this allows you to do is break things up into steps, which are both logically useful and also can make it so we can cache parts of the build. And we also need the ability to chain outputs of one step into the next step in order to actually accomplish our goals. So we have the concept of pipes, and this is a way of taking certain outputs and sticking them into inputs of another piece of the execution. Also notably, plots use these things called proto-formulas. They are formulas with some extra features, and they end up getting resolved just into those base formulas. But they're easier to write because they allow for some more complex inputs, and it just makes it easier for you to work with. So a step of a plot might consist of many of these, but a single step would look something like this. So you'll see now we have a proto-formula at the top, and we also have an input that is no longer an ugly hash that would take you forever to type. It is instead a human-readable name. So in this case, we use catalog to denote that it is a catalog-type input, and then we provide a triple here that has the name of the input We've used a busy box that comes out of our Warpsys distribution, so we've named that as a URL to make it easy to have good namespaces. And we then provide the specific release, which in this case was 1.35.0, and then an item. That item value is free text. You could do whatever you want with it. For our particular distribution of software, we've standardized on using AMD64 for that architecture, and then -static to show that this is a statically linked binary. Then everything else is basically the same. The exec and outputs work the same way. We get the same result. But now we can use these names instead of having to sling hashes all over our definitions. But the other thing we can do is have another step. So we could have a step 2 in this plot, and this is also a proto-formula, and it looks very similar. The one difference here is we now have mounted the result of step 1 at the path /step1 by using a pipe. And there we're specifying that it's a pipe. We should pipe in from step 1 the output hello world. So this allows you to now combine a whole graph of execution, many different parts. Another notable thing with Warpforge is it actually resolves this graph for you. So if you get a bunch of steps with a bunch of dependencies, it will figure out what execution order has to happen. And if you build yourself an impossible cycle, it will fail, saying, no, well, I can't build that. It's not possible to do that execution order. It'll notably fail before you attempt to execute it, which might save you quite a bit of time. So just to show a full plot, there's a bit more to it. It's a JSON object. And one of the real key approaches here is to describe everything as data, so we don't really care about how you're templating these out. But the full plot looks pretty similar. We see some more features here. We can, if we want to, mount things from the local file system. This is not a good idea if you're trying to do repeatable builds, because now there is definitely a dependency on your host system. But sometimes you do want to run something on files on your host system, so it can be useful. It's also useful for testing sometimes, to be able to pull in arbitrary file systems. And the steps, again, just sort of go together in this steps map. Notably, it's a map, not a list. It is not ordered. We determine the order based on what order things need to run in order to produce the outputs you've asked for. And this particular one is kind of simple. It has no outputs, which is maybe questionably useful. But you could also do like a RW mount if you wanted to actually work in a local directory, or you could spit out outputs to tarballs. The last concept here, if you're looking at our list of 3 things, is modules. This is pretty simple. It's just to attach some metadata. Often this is things like who authored this and what collection of packages it's part of. It also notably attaches the name, so whenever you're using a catalog, this name is the name that's going to be used. And you can actually put whatever metadata you'd like in here. We have a free text string map. So let's say you have license information you want to include, or maybe a website you want to link to, or whatever it is. All of that's available as free text, depending on how you want to build your catalogs. Speaking of catalogs, we've seen them in use a little bit. We've talked about plots, and I kind of nebulously said, here's a magical string that will look up this item. We are hoping that we can build a system that means people can centralize, do not need to centralize and build massive catalogs themselves. Instead, we can coordinate with each other and build things with namespacing so that you can decentralize these catalogs and have software that's built by multiple parties. And to do this, well, we need a naming system that will work at scale with many different parties, and also a way of actually sharing the data that will work at scale with many different parties. And that brings us to catalogs, which I will hand over to the other Eric to discuss in detail.
Thank you, sir. All right, so, and a change in background slide color because lots of diagrams. So catalogs are something we've referred to a couple of times. Now I'm going to dive deep on what that's all about. Catalogs are how we attacked, and I hope solved, the naming problem in this system. If you have worked in decentralized system development for any amount of time, you have probably discovered that there is a naming problem in your system in some form. Human beings have a hard time dealing with hashes. They're an incredibly useful foundational data structure, like Git is good because it is aggressively content addressed in the bottom of the design, right? That's a critical choice, and it works really well. But imagine trying to use Git with just like the git tree hash commands and having no concept of branches or tags. It would not work well, right? You would not accomplish things with that system. So we had the same discovery as we're building Warpforge. Content-addressed data structures and content-addressed instructions for computing things, very useful primitive. You still need something kind of attaching names to this at the top in order to make it usable. So we're going to introduce a whole data structure for that called catalogs, and they're going to solve this name-to-hash mapping problem. And we're also going to dial up the complexity and the challenge for ourselves pretty much to the top, because we have this strong interest in the system in reproducibility. You saw the reproducible builds logo on the slides earlier. You see it on my shirts as well. It's a major emotional commitment. We want to make sure anytime there are names involved in a system and you're doing that name to hash lookup, that name resolution process is itself deterministic, reproducible, extremely auditable for all time. So the giveaway is there's going to be a Merkle tree, and we're going to insist that the root hash of that Merkle tree is also covered by the root hash over a plot. And as long as you've got something encompassing both of those, you're going to have a good time. But we'll also dive a bit more now into this data structure in detail. Partially, this will be to show you how it works exactly in Warpforge. Partially, this will be a pitch for how to design Merkle trees in general, which I will hope will be reusable to people building their own systems. This whole data structure that is diagrammed on the left here is an IPLD native structure. So it's blocks of data, serialized, hashed, linked by hash. Don't worry if the diagram is too small to see. I'm going to go over it step by step in the next couple of slides. So we've built a somewhat hierarchical system here to contain different concepts. We're going to worry about having this structure encompass many different authors, and then many different versions of things. And then we, at some point in our domain, had to deal with like machine architectures, so we needed more metadata to discover that problem. And we're going to represent all of that in this structure. At the very top level of this catalog concept, we're worried mostly about different modules and things that may have been produced by different authors. So at that level, it's just going to be a huge map. The map is from a human-readable name to more data, a hash that will link to smaller parts of this document. But it may be a huge map. If you look at other systems that are doing big pieces of architectural work, like if you look at a Linux distro like Debian, it's got a few packages in it. It might have 250,000 packages in it. So we need this map to be capable of containing a lot of data. So we can't just throw one giant JSON blob at this problem and call it a day. I mean, we could, but like, let's not. It won't scale well. So we're at IPFS Camp here, so I'm going to have to just briefly shout out to one of the IP star technologies. We use IPLD for this data structure, and we use something called an advanced data layout for this data structure. An advanced data layout, and I'll just beg you to type that into the search engine of your choice and find the IPLD docs for it, is something that acts semantically like a simple data structure, like a map, and may have sharding internally. So our preferred data structure for this is a Prolly tree. It's sort of like a combination of a Patricia tree and sharding and B+ and hashing all at once. Has a bunch of very nice properties. You could also have solved this problem with a hamped. We don't worry about this too much in Warpforge. We just try to grab an off-the-shelf library that handles this big map component. This is a great reason to use IPLD, because we got to ignore that problem. Now, that top-level map points at a data structure specific to Warpforge called a module. This contains the human-readable name for things. So foobar.org/frobber, you can munge this string however you want. It's just a string. Because we're still in IPLD and Merkle tree construction land, this is going to point to deeper parts of our information. We'll have just a map of CIDs that have a version label, something like v2, v3, whatever, and we'll point to another document which will contain more. And we've got room to attach some metadata here, like authorship, licensing, etc. This next level down, where we have releases, again, we have to have a name attached. This is free text. Usually it has a V in it and then some numbers. And it will contain another map of more data. It'll have string values as keys again, and also string values or CIDs as the values. In our system, that is going to point to a file system hash. This is where you finally get to like solid stuff, yay. And you can attach another map of free text metadata to this for extensibility purposes. We won't spend a lot of time on that. But with one exception, there will be one piece of metadata, which will be another CID and will have a very important purpose. This third part of the tree is just a map of, like I said, item labels to typically a file system hash. We use this for architecture tuples. It's still a free text string, but as we tried to like build the universe and have it execute in Warpforge, we found architecture exists and is a thing we have to describe. So here it is. Now, every part of this document, again, connected by CIDs. It's just one huge, nicely structured, fairly typed Merkle tree. And we have names that will index across this whole thing. We decompose the names into like the different kinds of jump across the structure. But as long as you have that name string and you have the hash at the very root, reproducible resolve, it will produce that thing at the end of the item label list. Now, if you've been thinking about, through all this time, where's the authentication? How do I update this? How do I control who can update this? You don't. Or at least that's not in the picture. So we're worried about having integrity in this structure, and we're worried about having reproducible resolve when you start with that root hash. And we really focused on that. And then we stop right there intentionally, because we want to allow the authentication and the update control system to actually be pluggable. We want to let people solve this in possibly various ways. We want people to have policy control over this on their local machines. You could have a PKI thing here with signatures. That'd be great. You could have some sort of a chain of blocks on the top. Fine. Transparency logs, please. Or as a very degenerate but totally functional thing, you could have this whole data structure serialized on your local disk and say, what's on my local disk is authoritative. If this sounds a bit familiar to, like, say, Git again, where you can just have your local file system state be authoritative, and that means you can work locally without synchronizing with anyone, yeah, that's on purpose. That's a good feature. So, as I mentioned, although this is an IPLD native data structure and it's just a Merkle tree, we do also have a standardized way of projecting this into a file system, which is intentionally easy to put in a Git repo and walk around with shell commands. It's a convenience thing. By standardizing the heck out of this data structure, we also have gained the ability to make some other standardized tooling around it. For example, in Warpforge, we want people to be able to not just build stuff, but share it. And so we've built, for example, a website generator where anything that you have tracked in this catalog structure by doing a Warpforge build and then saying catalog, add release, et cetera, you could also then say Warpforge catalog generate site, and it will. We have produced a bunch of data already for some example stuff we've packaged. And there is a URL on the screen there, catalog.warpsys.org, which contains approximately what's in the screenshots. It's cool, it's navigable. It's even navigable on mobile. But now there was one thing I mentioned and then sort of skipped on real fast that I want to come back to. I said there was one piece of metadata in a catalog that is extra interesting. And this thing is called a replay. It's attached by CID link to the rest of the catalog. And it's kind of off to one side, but it's really important. We're interested in these reproducible builds, right? So every time you build something in Warpforge, you've written this declarative JSON structure that says what you wanted to do, and then Warpforge executed it. But if you want somebody else to be able to do that again, really you just have to share that declarative JSON document, right? So we've automated that. This should not take any human effort at all. It should just be built into the tool so everyone does it all the time. when you do Warpforge catalog add release, we're going to save that plot, that declarative JSON of what is being done in the release metadata. This isn't honestly all that magical. It's just really important to do it. So this piece of data gets frozen and attached to the release, fits into the whole Merkle tree. That's it. And remember we said it's very important to us that every time there's a name resolution process that is reproducible given that you have the same catalog root. We're freezing the plot JSON in the metadata where it's covered by the hash of eventually the catalog root. So if you've got one catalog root hash, you can look up every build instruction in it, and even though they're stitched together by human readable names, you can recursively resolve everything. Total explainability, total audit logs. This is honestly, I hope, the solution to Thompson attacks, trusting trust, etc. Every time you release something, yeah, I already said this, sorry, got excited. So the semantic implications of this replay data structure is truly rebuild anything, recursive explanations, having a total bill of materials for what you needed to build anything. All of it is ready to execute with minimal human intervention again. There's also one subtle detail about how we put this together that is different than, I think, any other system to date. So if you're mentally comparing this to other build tools, perhaps you've heard of Bazel, the open source one, Nix, various other tools like this that might have at least heard of recursive build descriptions. There are some out there. The way we've strung together this Merkle tree and Warpforge means you can start anywhere with your rebuilding or your explaining, and you can pause at any point. Because every plot has a snapshot of file systems and the content as the input, and a snapshot of file systems and the content as the output, you can reproduce and audit that step. You can also look up the reference to the things that produce that content, and you can recurse. You can walk in any direction in this graph, and you can pause at any point. As long as you can fetch that snapshot of data, you can resume partway through the graph. This means if we build really large graphs of systems, we have an easy time, actually. We can view things as having this complete dependency graph, but we have really no difficulty at all bootstrapping. Other systems, when you try to build the entire universe at once, you're going to end up with a very snarly thing somewhere down in the bootstrap area. And we also see in systems like Bazel, for example, it does a lot of things right. It has declarative builds as a core concept. That is good. But because there's no content-addressed like data checkpointing, and I don't think they have anything really comparable to this catalog data structure, which is meant to be shared with others, these systems seem to end up de facto requiring that you're coordinating in a monorepo. I hear this from basically everyone who uses these tools, even people who love these tools. They will say, yeah, we have our company repository, and it contains all the build instructions, and it works great for us in our organization. No, we can't share that with you. Sorry. That's a bummer. In Warpforge, I'm hoping we get away from this. Because build descriptions in Warpforge always depend on content, and they can attach this information about how to recursively build, we have much, much more freedom. We have this freedom to pause and resume the build process wherever we like. It's much, much easier for us to stitch together graphs where different people have owned the instructions in different parts of the graph. It's relatively easy to update freely your references to what else you've included, or don't, keep it frozen. And something that is a very surprising outcome of this is the way we've stitched the name and the hash lookups together. We can actually describe cycles in the build graph. This is weird. You can actually, if you have a compiler that is sufficiently deterministic, you could have the compiler take its own source code and compile the compiler and produce the same hash result. And you can still describe that in the catalog data structure. I believe this is unique to the field. So if you've been wondering, are there other package managers that do this or do close enough things? There are some that come close, but I hope this last couple of slides has suggested some novel innovations as well. I would also say, in general, package managers tend to involve solving a series of problems. There's transporting the data, there's having some lock files, there's selecting versions, And then there's usually some opinions about the interior of the packages. So like NPM packages have a different internal file structure than Go packages, etc. Some of these are meaningful problems and are different per different tool chains for a reason, and I would never argue with that. But these first two, transporting data, it'd be nice to solve that problem once if we could. Having lock files in the dark history of many years, I think package managers have argued about whether or not lock files are a good idea. I think that argument is over now, and we can definitively move on. Yes, lock files are good. I think at this point it should even be obvious, yes, lock files based on hashes are good, and everyone should have them. If we can solve that problem once, I think that would be amazing and handy, especially if we can solve it once in a way that gives us some of these superpowers like recursive explain. So in order to make Warpforge usable today, we're building stuff and trying to solve these problems as we go. Possibly we would like to look into building some bifrosts, I would call them, in the future to bridge other package managers into Warpforge, like just take the selection algorithms that they've already got and then turn that into lock files and proceed, so that we could get the reproducibility, the catalogs, the recursive explain, et cetera, while still reusing other tooling. I would also love it if we could turn some of these like transport components of Warpforge into a library that others could grab if they are so inclined. Nobody would be required to do so, but if it saves somebody time, that would be nice. So, you want to grab this?
Sure, yeah. So just kind of closing out here, why are we building this thing, and why are we building this thing now? I think the fundamental point here is that we want computers to do things that are repeatable and reliable and predictable and happen the same way every time. And that's a hard problem to solve. Some of the bugs that we run into, there's some where you get things like kernel dependencies. There also seems to be some where you get things like hardware dependency. So it's not an easy problem to fix, but better tooling means we can better detect these types of issues and patch them and sort them out. Other build tools, well, some of them are just straight up hard to use and are not really developer-centric. If you've spent a lot of time with Jenkins, you've probably gone through some beating your head against making it actually build things in a reliable way. I know I have. And very few do actual hermetic operations, so really enforce that, no, you must run this in a container or in some environment that will not leak or minimally leak things from your system. When we get into content addressing, and obviously, we're talking about moving towards being able to do the type of stuff on IPFS, hashing becomes very important. If you want to be able to build something twice and actually know it was built twice, you need to use hashes all the way through the system. And this morning, talking about the compute over data at scale in a distributed way, yes, there's the software that you want to run on there, but there's also all the software underneath it, right? If you want to run a Python script, that's great. You're going to need Python, and you're going to need a bunch of system software and libraries that make Python run. So if you can't take all that, hash it, repeat it, it becomes very hard to verify that two operations were actually done the same. If something's one byte off, it will mess up everything. So it's really a foundational element for being able to do those types of operations. From the security standpoint, and we've been a little bit quiet on security applications thus far, just because while they are interesting and they definitely exist and are relevant, they're not our first or target market, I'd say, but there is the whole concept of software bill of materials. They're becoming something that people care about quite a lot. There was the whole Biden executive order that was mostly about software bill of materials. And yeah, when you look at things like rootkits, things like on trusting trust and can you trust your C compiler, it can be quite difficult to do that on a modern system. At least we provide some way of freezing something you trust such that you can do it again. It doesn't fully solve all the problems, but it provides you with some features and some level of trust over the software you're building. So just to review, you can build stuff with Warpforge. We are building stuff with it today as trying to build up system software and trying to do some dogfooding with the tool internally, of course. And we're looking to build out that that set of packages and also get more people on board. The builds that you do, you can instantly test repeatability. You can run it again and very quickly see, yep, the hashes match, I'm good to go. You can also do things like, does it build exactly the same on my system and in my CI environment, which is not always a given. And you can also force other tools to be repeatable. So this is one thing we've had building certain tools that they aren't going to come out the same way every time, and we have to figure out what patching would have to be done to make that so. So of course, we're looking for folks to both help kick the tires on this tool and also to help increase the size of the Merkle tree of thingies we're building out, whether that be in our catalog of packages that's called WarpSys, or whether that be in your own catalog of packages you wish to publish, because it doesn't matter. You can use them interchangeably with the layout of that catalog system, which is quite nice. But that's our introduction to the tool, and thanks for coming out. Great to be able to present this to people finally. We have a few URLs for you. So the first one is the source code. It's a Go. It's the actual tool itself. Below that, you have the WarpSys org, which contains both the code that's used to build the catalog for WarpSys and then also the catalog itself. And then lastly, you have that catalog site. If you haven't checked that out, it works lovely on both mobile and desktop, so you can take a look at what that looks like. One last thing we're missing from here is we do have a chat on Element on matrix.org, right? So if you want to talk to some of us and you don't catch us in person, or some people that can't be here, that's Warpforge, #Warpforge on matrix.org. But otherwise, I think we have a little bit of time left, so we can open up to questions. Thanks again for coming out, and looking forward to talking to you as the conference goes on. Thanks.